Hey guys, so this video is going to be on the reflection and refraction of light. And so reflection you probably are familiar with. If not, it's fairly straightforward. Refraction's a little bit trickier, but we're going to talk about both of these. Okay, so this is what happens when light interacts with material. So light comes in and it hits something, and it could do one of two things or possibly both. It could reflect off the surface, or it could travel through the material and get bent, and that's what refraction is. So let's look at reflection first. So we have these red arrows. So we have this, so this is supposed to be a light beam. Okay, so you think of a light beam coming in. So we have a light beam come in, and we notice that it makes an angle with respect, respect to the surface, but it also makes an angle with respect to what we call the normal. Okay, so normal, when we talk about normals in physics and math class, what we mean is a line that's 90 degrees with respect to another line. So we say that this line is normal with respect to the surface here. So the light comes in and it's going to hit at a certain angle from this normal. And so we'll call this theta 1. Okay. Sometimes this is called the angle of incidence. Okay, the angle of incidence. So let's go ahead and write that down. Angle of incidence. Okay, so this is the angle that the light hits the surface relative to this normal, this perpendicular line. And then it's going to bounce off. And it's going to bounce off at an angle, which we'll call theta 2. Okay, and so this would be the angle of reflection. And so when we talk about reflection, at least normal reflection, it's it's fairly straightforward. What this says is that the angle of incidence, so theta 1, has to equal theta 2. Okay, whatever angle relative to the normal the light comes in at, then that's the angle relative to the normal it's going to reflect at. Okay, so angle of incidence equals angle of reflection. Okay, that's pretty easy to keep straightforward, right? So these two angles have to be equal to each other. And if we have a smooth surface, we would have, sorry about this, if we have a smooth angle, these light rays would all come in, sorry, a smooth surface, all these light rays would come in, they'd all reflect off kind of parallel, right? And so when we have a mirrored surface, light reflects off of it, it all goes in the same direction, and we see our image. Whereas if, say, the surface was a little rough, okay, the light comes in, and it's always going to reflect normal, so maybe that goes that way, and maybe the light comes in parallel, it hits this way, and maybe it comes off that way. And so what we can see is that these light rays will bounce off in various directions and they'll be scattered. So that's why most things you can't see like the image. You can't see the reflected image unless it's like, say, a piece of glass, in which case, or a piece of metal, in which case it's very smooth. Okay, so very smooth surfaces allow this reflection of the light in parallel lines, which means that they're going to form an image when you see them. But as far as the mathematics go, that's all there is to reflection. The angle of incidence is equal to the angle of reflection, and the angle that we're measuring is this angle relative to this normal line. Okay, so not too bad. Now refraction is a little bit more interesting. So what happens in refraction is we'll have light, traveling through a material, and very often the material is going to be air. So we have light traveling through the air, and then it hits something. It could hit a piece of glass, it could hit a piece of plastic, it could hit water. Okay, and when it does that, it's going to go from one material like air that it has one speed on and enter another material that has a different speed in. Okay, and when it does that, it gets bent. Okay, so you'll see right here, okay, the light comes in and it's going in this direction, but it gets bent up like that. Okay, and this is what we're talking about with refraction. It's this bending of light as it travels from one material to another where they have different speeds. And the amount it bends is determined by something called the index of refraction of the material. So we say that the index of refraction is n. Okay, so index of refraction would be n. Okay, and we can calculate n. We can say that n is equal to the speed of light in a vacuum, and that's our constant c. So speed of light in vacuum. Okay, so this is, in the absence of air, it's just like in deep space. So it's the speed of light in a vacuum, c, divided by v. Now v would be the speed of light in the material. And the speed of light in a material will be slower than it is in a vacuum, which means that this index of refraction for a material will always be greater than 1 because this top will always be more than the bottom. Remember, this top will be 2.998 times 10 to the 8th meters per second, and the bottom is whatever the speed is in the material. So the greater your index of refraction, the more light gets slowed down as it goes through the material, and the more it actually gets bent as well. Now, different colors, different wavelengths of light travel at different speeds as well. So red light travels at a different speed than blue light as it goes through water or glass or so on and so forth. And that's why prisms work the way they do, because the red light has a slightly different speed than the blue light, and the green light has different speed than it. So each color, each wavelength has a slightly different speed, and they get bent differently, and they get spread out. Okay, and that's how we can take white light, which is the combination of all light, and we can see rainbows. Okay, because different colors have different speeds of light and material, and they get bent by different amounts. And so the question is, okay, fine, they get bent by different amounts, but this is physics class, Dr. Melly. We want to do calculations. We crave math. I know you guys do. Okay, so what is the mathematics of this? Okay, so the mathematics is fairly straightforward, but there's a little trick. I believe in you guys. I think you can do it. So it comes about in Snell's law. Okay, so once again, we'll have our normal line, and this normal line is perpendicular to the surface. Okay, so we're going to run that kind of straight through, and we're going to do it over here too. Okay, so we're going to do, so this is going to be a normal line 90 degrees to the surface. And so the light will come in at theta 1, and then it gets bent, and now the angle is going to be different. Okay, theta 2. So theta 1 is the angle that makes the normal before it enters the glass, and theta 2 is the angle it makes after it enters the glass. And it turns out that the index of refraction of glass is greater than the index of refraction of air because light travels more slowly through glass. Okay? So when light enters a material, and travels more slowly, so it slows down, it gets bent towards the normal. It gets bent towards the normal line, and we can see that here. Okay, back. It gets bent towards this normal line, so it goes in along here, and then it gets bent towards it. Theta 2, okay, so this theta 2 is less than theta 1. Okay, so even if you didn't know that the index of refraction of glass was greater than that of air, just by looking at this, you can see that that's true. But just by noticing how the light gets bent through any material, you know if the speed of light is sped up or slowed down going through the material, and vice versa. We see this here. So here we would have, say, theta 1 as the first angle as it goes. Then it goes from glass to air, and then theta 2, and it gets bent away from the normal. Okay. So when light speeds up, it gets bent away from the normal. Sorry. I'm gonna have to go back here, aren't I? Sorry about that. Technical issues. Okay, so when light speeds up, it gets bent away from the normal. Okay, we can see that as it's going from glass to air. So what's the mathematical relationship that relates this? Well, it turns out that if we take the sine of theta 1, so the sine of the angle as it enters the material, and divide it by the sine of theta 2, the angle after it enters the material. And again, these are angles with respect to the normal line. This is going to be equal to a constant. These are always going to be equal to the same number. And it turns out this number is going to be the index of refraction of the second material divided by the index of refraction of the first material. Okay? So maybe to simplify a little bit more, we have sine theta 1 over sine theta 2 is equal to n to the index of refraction of substance 2 divided by the index of refraction of substance 1. And this is Snell's law. Okay? So if, say, I give you the two angles, and I give you the index of refraction of one material, you can find the index of refraction of the other material. Not bad, right? But then what that allows you to do is if you know the index of refraction, you can find the speed of light in that material, and that's kind of cool. Okay, so that's kind of cool. So you can use this, and just by using the angles and Snell's law and this definition of index of refraction, you can actually determine the speed of light in material without using some silly stopwatch or using some high-tech equipment or anything like that. Just using mathematics, you can calculate the speed of light in material. And I think that's pretty nifty. So anyway, I hope this makes sense, and let me know if you have any questions.